On July 1st, 2025, at precisely 14 hours 37 minutes Universal Time, the Atlas telescope in Chile detected something unusual. The automated system flagged a faint dot moving against the stars. Within hours, astronomers realized this wasn't just another asteroid. The calculations were unmistakable. This object was moving too fast to belong to our solar system. The discovery sent alerts through the astronomical community's rapid response networks. Observatory after observatory confirmed the same thing. The object's path was hyperbolic, meaning it came from another star system entirely. This was only the third confirmed interstellar visitor to pass through our cosmic neighborhood. They designated it 3I/ATLAS. The 3I marked it as the third interstellar object ever confirmed. The ATLAS honored the telescope that found it, but names hardly captured what this discovery meant. We were witnessing a chunk of another solar system, formed around a distant star, now passing through our own. The first measurements revealed extraordinary characteristics. The object was traveling at 130,000 miles per hour. That's 170 times faster than a rifle bullet. At that speed, it could cross the United States in under 3 minutes. This wasn't just visiting our solar system. It was racing through like a cosmic missile. The trajectory calculations showed something remarkable. 3I/ATLAS would pass between Earth and Mars, threading through the inner solar system with perfect geometry for observation. Its closest approach to the Sun would occur on October 29, 2025. We had just months to study this visitor before it disappeared forever. What made this discovery special wasn't just its interstellar origin. The timing was nearly perfect. Unlike Oumuamua, which we discovered as it was already leaving, 3I/ATLAS was still approaching. We had time to mobilize our best telescopes. We could plan coordinated observations. We could gather data no one had collected before. The Atlas survey system that found it was designed to protect Earth from asteroids. 4 robotic telescopes scan the entire sky every 2 days, looking for rocks that might threaten our planet. Finding an interstellar visitor was like fishing for trout and catching a deep-sea creature instead. The system worked perfectly, but the catch was beyond anyone's expectations. Within 48 hours, every major observatory on Earth had 3I/ATLAS in their sights. The Hubble Space Telescope adjusted its schedule. The James Webb Space Telescope prepared for observations. Ground-based telescopes from Chile to Hawaii began tracking this cosmic wanderer. The scale of response was unprecedented. The early data revealed a fuzzy cloud around the object. This wasn't a dead rock like some expected. It was active, releasing gas and dust as the sun warmed its surface. The coma, as astronomers call this cloud, suggested frozen materials were sublimating, turning directly from ice to gas. This visitor was waking up after millions of years in the cold between stars. The implications rippled through multiple fields of science. Planetary scientists saw a chance to study material from another solar system. Chemists wanted to analyze its composition. Physicists hoped to test theories about how objects survive interstellar journeys. Everyone understood this was a rare opportunity. The discovery of 3I/ATLAS marked the beginning of an intensive campaign that would last months. Every observation would be precious. Every measurement would matter. We were about to learn what happens when a piece of an alien solar system encounters our sun. The universe had delivered a mystery to our doorstep, and we had limited time to solve it. The numbers alone told us 3I/ATLAS was extraordinary. Moving at 130,000 miles per hour through our solar system, it traveled faster than any natural object we'd tracked before. This wasn't the lazy drift of a typical comet. This was an object with somewhere urgent to be, carrying momentum from another star system entirely. The speed created immediate challenges for observers. Ground-based telescopes had to track at rates that pushed their mechanisms to the limits. The object crossed the field of view so quickly that long exposures became impossible. Astronomers had to adapt their techniques, taking rapid sequences of shorter images instead of their usual patient observations. But speed was only part of what made 3I/ATLAS unusual. Its trajectory was threading a needle through the inner solar system. The path would carry it between Earth and Mars orbits, passing at distances that seemed almost deliberately chosen for optimal observation. Not too close to be dangerous, not too far to study. The universe had delivered this visitor on a silver platter. The perihelion, its closest approach to the Sun, would occur on October 29th, 2025. At that point, 3I/ATLAS would be about 130 million miles from our star. That's between Earth's orbit and Mars's orbit, a region where solar heating becomes intense enough to activate a comet, but not so intense that it destroys the nucleus. Size estimates varied wildly in those early days. The nucleus, the solid core of the object, was hidden inside its own glowing cloud of gas and dust. Hubble's best images could only set limits. Somewhere between 320 meters and 5.6 kilometers across. That's anywhere from a large building to a small city. The uncertainty frustrated scientists used to precise measurements. The observable window was both generous and cruel. We had discovered 3I/ATLAS while it was still approaching, giving us months to prepare. But the cosmic geometry would play a trick on us. Just as the object reached its most active phase near the Sun, Earth would be on the opposite side of our star. For 2 crucial months, 3I/ATLAS would be hidden in solar glare, invisible to every telescope on or near Earth. This blackout period felt like a cosmic joke. The time when solar heating would drive the most dramatic changes, when the nucleus temperature would peak and activity would climax, would be completely unobservable from our planet. We would see the approach and the aftermath, but miss the main event entirely. The December reappearance would mark our last chance to study 3I/ATLAS. By then, it would be racing away at even higher speeds, growing fainter each night. The observation window would shrink rapidly. Every day of delay would mean significantly degraded data quality. Time was our enemy in this cosmic chase. The early morphology was puzzling too. Most comets develop distinctive features as they warm up. A bright coma surrounding the nucleus, jets of gas shooting from active regions, and a tail swept back by solar wind. But 3I/ATLAS seemed reluctant to follow the textbook. Its coma was compact and oddly shaped. The tail, if it existed, was barely visible. Amateur astronomers, hoping to glimpse this interstellar visitor, faced disappointment. At its brightest, 3I/ATLAS would reach only magnitude 11 or 12. That meant it would remain invisible to the naked eye, requiring substantial telescopes to see it all. There would be no spectacular sky show like Hale-Bopp or Neowise. This visitor preferred to keep a low profile. The timing, critical nature of the observations created a frenzy of activity at observatories worldwide. Telescope time, usually scheduled years in advance, was reorganized on weekly timescales. Regular research programs were disrupted, but everyone understood the stakes. This was a chance that might not come again for decades. The James Webb Space Telescope represented humanity's most powerful tool for understanding 3I/ATLAS. Floating at the second Lagrange point, a million miles from Earth, Webb's infrared vision could peer through cosmic dust and decode chemical signatures invisible to other telescopes. On August 6, 2025, it turned toward our interstellar visitor. Webb's preparations had begun weeks earlier. The observation planning was complex. The telescope had to track a fast-moving target while maintaining its precise pointing stability. The infrared detectors needed specific configurations to capture the faint spectral signatures of gases in the coma. Every detail mattered for this unprecedented observation. The near-infrared spectrograph was the key instrument for this investigation. NIRSPEC could split light into component wavelengths with extraordinary precision, revealing which molecules were present in the coma. Each molecule absorbs and emits light at specific frequencies, creating fingerprints that identify chemical composition. Webb would read these fingerprints like a cosmic detective. The coordination required was remarkable. Webb's observations had to align with data from other telescopes to create a complete picture. Hubble would provide high-resolution visible light images. Ground-based observatories would track the object's position precisely. SphereX would map the extent of gas emissions. Each telescope contributed a piece to the puzzle. Scientists expected Webb to detect the usual suspects in the comet's chemistry. Water vapor should dominate, with carbon monoxide and carbon dioxide as minor components. Organic molecules might appear in trace amounts. The ratios would tell us about the temperature and pressure conditions where 3I/ATLAS formed billions of years ago. These were reasonable expectations based on decades of comet studies. The infrared advantage was crucial for this kind of work. Many molecules are invisible in optical light, but shine brightly in infrared. Webb could detect gases at concentrations measured in parts per million. It could distinguish between different isotopes of the same element. This level of detail was impossible from ground-based observations. The team analyzing Webb's data included experts from multiple countries, spectroscopists who understood molecular physics, planetary scientists who studied comet formation, and cosmochemists who traced the origins of chemical elements. This wasn't just astronomy. It was detective work on a galactic scale, piecing together clues from an alien crime scene. Webb's ability to observe 3I/ATLAS was limited by geometry and time. The telescope could only point so far from the Sun without risking damage to its delicate instruments. As 3I/ATLAS approached perihelion, it would enter Webb's exclusion zone, becoming unobservable. The window for infrared spectroscopy was narrowing with each passing day. The first raw data from Webb arrived at the Space Telescope Science Institute in Baltimore. The processing pipeline converted digital signals into spectra. Quality checks ensured the observations were clean. Then came the moment of truth. Scientists would see for the first time what molecules were streaming from this interstellar visitor. The expectations were high, but measured. Previous interstellar objects had surprised us. Oumuamua showed no detectable gas emissions at all. Borisov had unusual carbon monoxide levels. Would 3I/ATLAS follow known patterns or reveal something entirely new? The infrared spectra would hold the answer. What made this observation special wasn't just Webb's technical capabilities, it was the timing. We were catching an interstellar object while still approaching the Sun, still becoming active. Previous visitors had been studied too late or with less capable instruments. This was our best chance to understand what these cosmic wanderers were made of. The analysis would take days, maybe weeks. Spectroscopy isn't instant gratification. Each spectral line had to be identified, measured, and verified. Contamination from Earth's atmosphere or instrumental effects had to be removed. But somewhere in those infrared wavelengths lay the chemical truth about our interstellar visitor. The spectrum from Webb revealed something no one expected. Where water should have dominated, carbon dioxide ruled instead. The ratio was staggering: 8 parts carbon dioxide to 1 part water. This shattered every assumption about how comets should behave. In our solar system, water dominates comet chemistry by factors of 10 to 100. The Discovery team checked their calibrations 3 times. They compared with independent measurements. They consulted experts in molecular spectroscopy. The result remained the same. 3I/ATLAS was releasing carbon dioxide at rates that shouldn't be possible for an object of its size. This wasn't a measurement error. This was a genuine cosmic mystery. To understand why this mattered, consider how comets normally work. Water ice forms the bulk of most comet nuclei. As sunlight warms the surface, water sublimates directly to gas, creating the visible coma. Carbon dioxide exists too, but as a minor component. Finding a comet dominated by carbon dioxide was like finding an ocean made of sand. The implications rippled through multiple theories of planetary formation. In our solar system, carbon dioxide ice forms in specific regions of the protoplanetary disk. Too close to the sun, it vaporizes. Too far away, water ice dominates. There's a sweet spot, a carbon dioxide snowline, where CO2 can condense while water remains gaseous. Had 3I/ATLAS formed in such a zone around another star, the temperature physics made the mystery deeper. At 3I/ATLAS's current distance from the Sun, carbon dioxide should be actively sublimating. Water ice should be starting to activate too, but the spectra showed robust CO2 emissions with barely detectable water vapor. Something was suppressing water sublimation while allowing carbon dioxide to escape freely. Previous interstellar visitors hadn't prepared us for this. Oumuamua showed no gas emissions at all, remaining stubbornly inert despite passing close to the Sun. Borisov displayed elevated carbon monoxide, but still had plenty of water. 3I/ATLAS was writing its own chemical rules, ignoring the patterns we thought were universal. The spectral lines themselves were beautifully clear in Webb's data. The carbon dioxide signature at specific infrared wavelengths was unmistakable. This wasn't ambiguous or uncertain. The molecule's fingerprint was as clear as a photograph, but clarity and detection only highlighted the mystery of its abundance. Some scientists proposed that 3I/ATLAS might have a layered structure. Perhaps water ice existed in the interior, sealed beneath a carbon dioxide-rich crust. Solar heating could preferentially sublimate the outer CO2 layer, while leaving inner water ice untouched. This would explain the strange ratio, but required a formation scenario unlike anything in our solar system. Alternative explanations emerged quickly. Maybe 3I/ATLAS formed in an environment where carbon dioxide was simply more abundant than water. Some stellar systems might have different carbon-to-oxygen ratios that favor CO2 formation. Or perhaps billions of years of cosmic ray bombardment had chemically altered the surface, converting other molecules to carbon dioxide. The observation challenged our Earth-centric view of chemistry. We assume water dominates because it does in our solar system, but the galaxy contains hundreds of billions of stars, each with potentially different conditions. 3I/ATLAS was teaching us that our local chemistry might not be universal. Other stellar systems could have fundamentally different chemical personalities. The carbon dioxide discovery changed how we thought about interstellar objects. They weren't just visitors from other star systems. They were chemical ambassadors, carrying information about environments we could never directly explore. Each one expanded our understanding of what was possible in the universe. The mystery would deepen with the next discovery. If 3I/ATLAS was already breaking chemical rules with its carbon dioxide abundance, what else would it reveal? SphereX's Wide-Field Infrared Survey revealed something that made astronomers question their instruments. The carbon dioxide cloud around 3I/ATLAS extended for 348,000 kilometers. That's nearly 250,000 miles, larger than the distance between Earth and the Moon. The scale was absurd for an object with a nucleus only a few kilometers across. The physics didn't add up. A small icy nucleus simply couldn't produce enough gas to fill such an enormous volume. Even if the entire surface was actively sublimating carbon dioxide at maximum theoretical rates, the cloud should be 100 times smaller. Yet the observations were unambiguous. Multiple instruments confirmed the same impossible extent. To visualize this, imagine a tennis ball creating a fog bank the size of a city. The disparity between source and effect was that extreme. Every model of cometary outgassing failed to explain what SPHEREX was seeing. This wasn't just unusual. According to our understanding of physics, it shouldn't be happening at all. The distribution pattern added another layer of mystery. The CO2 cloud wasn't uniformly distributed around the nucleus. It showed structure, density variations that suggested complex dynamics. Some regions were denser, others more diffuse. The pattern changed over time, but not in ways that matched simple sublimation models. Scientists scrambled to explain the phenomenon. One possibility was fragmentation. Perhaps 3I/ATLAS wasn't a single solid nucleus, but a collection of smaller chunks, each contributing gas to the enormous cloud. This would multiply the effective surface area for sublimation. But Hubble's images showed no evidence of multiple fragments. Another theory proposed that we were seeing accumulated gas from weeks of activity. Maybe the CO2 wasn't being produced currently at extreme rates, but had been building up over time. The gas might be moving too slowly to dissipate, creating an expanding bubble that persisted far longer than expected. This required special conditions that seemed unlikely. The energetics were troubling. Maintaining such a massive gas cloud required continuous energy input. Sunlight alone couldn't provide enough power. Either 3I/ATLAS had internal heat sources, or the physics of sublimation worked differently than we understood. Neither option was comfortable for scientists trained on solar system comets. Interactions with the solar wind offered another explanation. Charged particles streaming from the sun could ionize carbon dioxide molecules, creating electromagnetic effects that accelerated the gas outward. This might explain the cloud's extent, but the process should be visible in other wavelengths. No such signatures appeared in the data. The impossible cloud forced astronomers to reconsider basic assumptions. Maybe interstellar objects behaved fundamentally differently from solar system comets. Billions of years in deep space might alter their physical properties in ways we hadn't anticipated. The usual rules might not apply to visitors from other stars. SphereX continued monitoring the cloud's evolution as 3I/Atlas approached the Sun. The extent actually grew larger, reaching nearly 400,000 kilometers at one point. This defied predictions that increasing solar wind pressure would compress the coma. Instead, the cloud seemed to have its own dynamics, independent of external forces. The spatial resolution of SphereX revealed filamentary structures within the cloud. Streams of denser gas connected different regions. These filaments evolved over days, forming and dissipating in patterns that suggested complex physical processes. This wasn't simple radial outflow from a nucleus. This was a dynamic system with its own weather. The impossible cloud became the signature mystery of 3I/ATLAS. While the carbon dioxide dominance was strange, the cloud's extent was physically problematic. It suggested either new physics or a fundamental misunderstanding of this object's nature. The universe was showing us something that challenged textbook knowledge. The Swift Observatory's ultraviolet and optical telescope detected hydroxyl radicals around 3I/ATLAS in early August. Hydroxyl, consisting of one oxygen and one hydrogen atom, typically forms when ultraviolet light breaks apart water molecules. Finding OH usually means finding water. The detection seemed to confirm that 3I/ATLAS contained the water ice that comets should have. But when Webb and SphereX searched for water vapor directly, they found almost nothing. The infrared signatures of water were barely above detection limits. The spectroscopic evidence was clear. Very little water was escaping from 3I/ATLAS. This created a paradox. How could there be hydroxyl without significant water vapor? The contradiction gnawed at researchers. In normal comets, the relationship between water and hydroxyl is straightforward. Solar ultraviolet radiation splits H2O into H and OH. The amount of hydroxyl tells you how much water is present. But 3I/ATLAS was breaking this reliable relationship. The chemistry wasn't adding up. Several explanations emerged, each with problems. Perhaps the water was there but trapped beneath surface layers that prevented sublimation. The hydroxyl might come from a thin surface film of water that produced OH radicals without releasing bulk water vapor. This would require an unusual surface structure that somehow allowed UV penetration while blocking gas escape. Another possibility involved alternative hydroxyl sources. Some organic molecules could produce OH when exposed to solar radiation. If 3I/ATLAS had an organic-rich surface, it might generate hydroxyl without significant water ice. But the specific organics required were rare, and the process wouldn't match the observed OH production rates. The temperature profile offered another angle. At 3I/ATLAS's distance from the Sun, water ice sublimation was relatively inefficient. Carbon dioxide, being more volatile, would dominate the outgassing. But this didn't explain the near absence of water. Even inefficient sublimation should produce detectable amounts, especially given Webb's sensitivity. The observation timeline complicated interpretations. Swift's hydroxyl detection came from integrated observations over several days. Webb's snapshot might have missed episodic water release. Perhaps 3I/ATLAS released water in bursts too brief or too infrequent for Webb to catch. This seemed unlikely, but couldn't be ruled out. Laboratory experiments with ice mixtures suggested another scenario. When carbon dioxide and water ice are intimately mixed at very low temperatures, the CO2 can form a matrix that traps water molecules. As the CO2 sublimates, it might leave water behind in a metastable state that doesn't easily vaporize. This had been observed in lab conditions simulating interstellar environments. The isotopic ratios could have provided answers, but measuring them in such a faint object pushed instruments to their limits. Different formation environments produce different ratios of heavy to light water. These ratios could reveal whether the water was primordial or had been processed by billions of years of cosmic radiation. The missing water became more puzzling when compared to other interstellar visitors. Borisov had shown normal water production for a comet its size. Even Oumuamua, which showed no obvious activity, hadn't presented this specific contradiction of hydroxyl without water. 3I/ATLAS was unique in its chemical confusion. Some researchers proposed that our detection methods were missing something. Perhaps water was being released in forms that didn't show up in standard spectroscopy. Ice particles too large to vaporize completely, or water bound in complex molecules that hadn't been considered. The absence of evidence wasn't necessarily evidence of absence. The water mystery connected to the broader puzzle of 3I/ATLAS's nature. An object dominated by carbon dioxide with minimal water didn't fit any formation scenario in our solar system. Either this visitor formed under conditions unlike anything we knew, or it had been altered by processes we didn't understand. As 3I/ATLAS approached perihelion, scientists hoped that increased heating would resolve the water question. Higher temperatures might break through whatever was suppressing water release. The December observations would be crucial for understanding this chemical puzzle. The universe seemed to be playing a game with us, sending 3 interstellar visitors that couldn't be more different. Each one challenged our assumptions in unique ways. Together, they painted a picture of interstellar space populated by objects far more diverse than we'd imagined. Oumuamua arrived first in 2017, like a cosmic riddle wrapped in stone. It showed no coma, no tail, no obvious signs of outgassing. Just a tumbling, elongated object reflecting sunlight in patterns that suggested a shape unlike any asteroid we'd seen. Its aspect ratio of 10:1 was extreme, more needle than rock. Then it began accelerating away from the Sun without any visible propulsion. The acceleration was tiny, but measurable. Multiple observatories confirmed it. Oumuamua was speeding up as it left our solar system, gaining velocity through some invisible process. Scientists proposed exotic explanations: hydrogen ice too pure to detect, a light sail pushed by solar radiation. Even suggestions of artificial origin emerged from serious researchers. Borisov followed in 2019, bringing relief to astronomers. Finally, an interstellar visitor that behaved like a proper comet. It developed a beautiful coma, sported a classic tail, and sublimated water ice, just as theory predicted. The only unusual feature was elevated carbon monoxide levels, suggesting formation in a colder environment than our solar system comets. The carbon monoxide excess in Borisov made sense within existing frameworks. CO requires colder temperatures to condense than water ice. Borisov likely formed in the outer reaches of its original star system, where CO could freeze out of the protoplanetary disk. This was strange, but not impossible, exotic, but not incomprehensible. Now 3I/ATLAS had arrived with its own unique personality, dominated by carbon dioxide in proportions that shouldn't exist, creating gas clouds too large for its nucleus size, showing hydroxyl without water in a chemical contradiction that defied explanation. Each characteristic seemed designed to confound our understanding. The progression was almost suspicious in its systematic challenge to our theories. First, an object with no visible activity but unexplained acceleration. Second, a normal comet with unusual trace chemistry. Third, a chemical impossibility with physics-defying gas production. The universe appeared to be methodically demonstrating our ignorance. Size comparisons revealed another pattern of diversity. Oumuamua stretched 400 meters long but only 40 meters wide, a cosmic needle. Borisov's nucleus measured about 500 meters across, typical for a small comet. 3I/ATLAS fell somewhere between 320 meters and 5.6 kilometers, its true size hidden in uncertainty. 3 visitors, 3 completely different physical scales. The orbital characteristics showed similar diversity. Oumuamua's trajectory suggested origins in the direction of Lyra, though its exact source remained unknown. Borisov appeared to come from the direction of Cassiopeia. 3I/ATLAS's path pointed toward origins in the galactic thick disk. 3 different regions of space, 3 different stellar neighborhoods. Discovery circumstances added another layer of variety. Oumuamua was found leaving, already past perihelion, when detected. Borisov was spotted approaching with months of warning. 3I/ATLAS was caught at the perfect moment, far enough out for preparation, but close enough for immediate study. The timing seemed almost orchestrated for maximum scientific diversity. The chemical signatures formed perhaps the starkest contrast. Oumuamua, no detectable emissions. Borisov, water dominated with CO enhancement. 3I/ATLAS. CO2 dominated with mysterious water depletion. If you were designing objects to show the maximum possible chemical diversity, you couldn't do better than these 3. Each visitor expanded the parameter space of what interstellar objects could be. Together, they suggested that our theoretical models, based entirely on solar system examples, were woefully incomplete. The galaxy contained varieties of cosmic debris that we hadn't imagined. Our sample of 3 was revealing vast diversity that probably represented an even vaster reality. The carbon dioxide dominance of 3I/ATLAS pointed toward formation conditions unlike anything in our solar system. To understand what happened required thinking about alien stars, different temperatures, and chemistry occurring billions of years ago in a cosmic environment. We can only model, never visit. Every star creates temperature zones in its surrounding disk of gas and dust. Close to the star, only rocky materials can condense. Further out, water ice forms. Even further, more volatile compounds like carbon dioxide and carbon monoxide freeze. These zones, called snowlines, determine what materials are available for planet and comet formation. In our solar system, the water snowline sits around 3 astronomical units from the Sun, roughly at the asteroid belt. The carbon dioxide snowline is further out, around 10 astronomical units, near Saturn's orbit. Beyond Neptune, even carbon monoxide can freeze. This creates a radial chemistry gradient that shapes the composition of everything that forms. But other stars create different patterns. A smaller, cooler star would have snowlines much closer in. A massive hot star would push them further out. The The zones would have different widths, different temperature gradients. The chemistry of planet formation would follow entirely different rules. 3I/A TLAS might have formed in such an alien configuration. The CO2 snowline is particularly interesting. It represents a sweet spot where carbon dioxide ice can condense while water remains vapor. Objects forming here would incorporate CO2 as their primary ice, with water as a minor contaminant. This matches what we observe in 3I/A TLAS: abundant carbon dioxide, minimal water. Temperature isn't the only factor. The chemical composition of the protoplanetary disk matters too. If the carbon-to-oxygen ratio differs from our solar system, different molecules become dominant. A carbon-rich disk might favor CO2 and CO over water ice. The initial ingredients determine the final recipe. Stellar evolution adds complexity. A star's luminosity changes over time, moving snowlines inward or outward. An object that formed in one zone might experience different conditions as its star aged. Billions of years of stellar evolution could alter the chemical environment dramatically. 3I/A TLAS might carry signatures of multiple epochs. The formation timescale matters too. In our solar system, comets formed over millions of years as dust grains stuck together in the cold outer disk. But formation rates depend on disk density, turbulence, and stellar radiation. Other systems might build comets faster or slower, incorporating different materials depending on timing. Radiation environment during formation leaves permanent marks. Ultraviolet light from the young star can photodissociate molecules, creating radicals that recombine in unusual ways. Cosmic rays can trigger chemistry that wouldn't occur otherwise. These processes might explain some of 3I/A TLAS's strange chemical signatures. The thick disk origin suggested by 3I/A TLAS's trajectory adds another dimension. Stars in the thick disk formed 8 to 12 billion years ago from gas clouds with different elemental abundances. Lower metallicity meant fewer heavy elements, potentially favoring simpler molecules like CO2 over complex organics. Ancient chemistry for an ancient visitor. Laboratory experiments have tried to replicate these alien conditions. Scientists create ice mixtures at temperatures near absolute zero, bombard them with radiation, and slowly warm them to see what happens. The results often surprise. Chemistry at extreme conditions doesn't always follow intuitive rules. New molecules form, unexpected structures emerge. The isotope ratios in 3I/A TLAS could tell us the temperature at which its ices formed. Different temperatures produce different ratios of heavy to normal carbon and oxygen. These ratios are like thermometers frozen in time, recording conditions from billions of years ago. But measuring them in such a faint object pushes our instruments to their limits. Understanding 3I/A TLAS's formation means accepting that our solar system isn't a template for the universe. Other stars create other chemistries, other conditions produce other objects. Each interstellar visitor expands our catalogue of what's possible when stars and planets form. Tracing 3I/A TLAS back to its birthplace meant diving into galactic archaeology. The visitor's trajectory, when reversed through time and space, pointed toward an origin in the Milky Way's thick disk. This wasn't just another region of space. This was another epoch of cosmic history. Our galaxy has distinct populations of stars, like geological layers recording different eras. The thin disk, where our sun lives, contains relatively young stars rich in heavy elements. The thick disk holds older stars from when the galaxy was younger and more chaotic. The stellar halo contains ancient stars from the galaxy's earliest days. The thick disk formed roughly 8 to 12 billion years ago, during what astronomers call the cosmic noon. Star formation throughout the universe was reaching its peak. Galaxies were colliding and merging frequently. The Milky Way was still assembling itself from smaller components. It was a violent, creative time in cosmic history. Stars in the thick disk move differently from thin disk stars. Their orbits are more tilted, more eccentric. They bob up and down through the galactic plane like dolphins through water. This distinctive motion pattern is preserved in anything ejected from thick disk planetary systems. 3I/ATLAS carried this kinematic signature. The velocity vector was the key clue. 3I/ATLAS entered our solar system at about 25 kilometers per second relative to the local standard of rest. This speed and direction matched the typical motion of thick disk stars. It was like finding an antique with a maker's mark that identified its era and origin. If 3I/ATLAS truly came from the thick disk, it had been wandering the galaxy for billions of years. When it began its journey, Earth didn't exist. The sun hadn't formed. The gas cloud that would become our solar system was still dispersed through space. This visitor predated everything familiar in our cosmic neighborhood. The chemical implications were profound. Thick disk stars form from gas with lower metallicity, fewer elements heavier than hydrogen and helium. This would affect the chemistry of any planets or comets forming around these stars. Different ingredients produce different results. The strange composition of 3I/ATLAS might reflect this ancient, metal-poor environment. Survival over such timescales was remarkable. For billions of years, 3I/ATLAS had endured cosmic radiation that would destroy most materials. It had survived close encounters with stars, passage through dense molecular clouds, exposure to supernovae. Yet it retained enough volatile ices to become active when warmed by our sun. The journey itself was mind-bending to contemplate. 3I/ATLAS had probably passed through thousands of star systems, spending millions of years in the darkness between each one. It had witnessed stellar births and deaths, planetary formation and destruction. It was a time capsule from an era when the universe looked very different. Statistical arguments supported the thick disk origin. Most stars in our galactic neighborhood belong to the thin disk, but the relative velocities favor encounters with thick disk objects. It's like two groups of cars on different highway lanes. The speed difference makes encounters more likely than if everyone traveled together. The preservation of primordial ices over such timescales suggested special conditions. Perhaps 3I/ATLAS had spent most of its journey in the darkest, coldest regions between stars. Or maybe it had a protective crust that shielded the interior from radiation damage. The survival mechanisms were as mysterious as the chemistry. Other thick disk objects might be passing through our solar system undetected. The galaxy could be full of ancient wanderers, each carrying chemical messages from the universe's younger days. 3I/ATLAS was just the one we happened to spot, a representative of a vast population of cosmic fossils. The thick disk origin remained a hypothesis, not proven fact, but it fit the available evidence better than alternatives. It explained the velocity, suggested reasons for the unusual chemistry, and connected 3I/ATLAS to the broader story of galactic evolution. October 29th loomed like a deadline written in celestial mechanics. On that date, 3I/ATLAS would reach perihelion, its closest approach to the Sun. But Earth's position would place our star directly between us and the visitor. For 2 months, 3I/ATLAS would vanish into solar glare, invisible to every telescope on or near our planet. The timing felt deliberately cruel. Just as 3I/ATLAS reached peak activity, maximum heating, and most dramatic changes, we would be blind to it all. The universe seemed to be hiding the climax of this cosmic performance behind a curtain of sunlight. We would see the approach and aftermath, but miss the main event. Astronomers scrambled to gather data before the blackout. Every observation became precious. Telescope time, usually scheduled months in advance, was reorganized on daily timescales. Regular research programs were postponed. The entire global astronomical community focused on extracting maximum information before time ran out. The solar conjunction wasn't just an inconvenience. It was a fundamental limitation of Earth-based astronomy. Our planet's orbit means that objects passing close to the Sun become unobservable for weeks or months. We can't point telescopes toward the Sun without destroying sensitive instruments. The brightest object in our sky creates the largest blind spot. Space telescopes faced similar constraints. Hubble couldn't observe within 50 degrees of the Sun. Webb had even stricter pointing restrictions to keep its delicate infrared sensors cool. Even spacecraft designed for solar observation couldn't track a comet against the Sun's overwhelming glare. Technology had limits that orbital geometry enforced. The September observations took on desperate urgency. Every spectrum captured, every image recorded, might be the last useful data before conjunction. Scientists worked around the clock, processing observations in real time to guide the next night's targets. Sleep became optional. Coffee became essential. Time was the enemy. Some creative solutions emerged. Mars would be in a different position, able to observe 3I/ATLAS during part of Earth's blind period. The Mars Reconnaissance Orbiter might capture images when we couldn't. Even distant spacecraft like New Horizons had different viewing angles that might provide data during conjunction. The last pre-conjunction observations came in late September. 3I/ATLAS was accelerating toward the Sun, its coma growing more active. The carbon dioxide emissions were intensifying. Changes were happening rapidly. Then, like a theater curtain falling, the visitor disappeared behind our star. The show continued, but we lost our view. The blackout period would last until early December. During those weeks, 3I/ATLAS would experience its most extreme conditions. Solar heating would peak. If the nucleus was going to fragment, it would happen now. If water ice was hidden beneath CO2 layers, maximum heating might release it. Critical events would unfold unseen. Computer models tried to predict what would happen during conjunction. Based on pre-conjunction observations, scientists simulated the thermal evolution, gas production rates, and possible fragmentation scenarios. But models were poor substitutes for actual observations. Too many unknowns made predictions uncertain. The waiting was psychological torture for astronomers. They had spent months intensively studying 3I/ATLAS, working to understand its mysteries. Now, at the crucial moment, they could only wait. It was like reading a mystery novel with the climactic chapters torn out. The story continued, but readers were forced to skip ahead. December's reappearance would bring either answers or deeper mysteries. Would 3I/ATLAS emerge unchanged, suggesting stable structure despite perihelion heating? Would it show dramatic alterations, revealing what intense solar exposure had done? Would it fragment into pieces or remain intact? The conjunction had hidden all the answers. The forced pause gave scientists time to analyze existing data more thoroughly. Details overlooked in the rush of observations could be examined carefully. Patterns might emerge from the noise. The conjunction was frustrating, but also provided breathing room for deeper analysis. The response to 3I/ATLAS showcased humanity at its collaborative best. Observatories worldwide synchronized their efforts, creating a planet-spanning network dedicated to understanding one small object racing through our solar system. National boundaries dissolved. Competitive institutions shared data freely. The entire astronomical community united with singular purpose. NASA's coordination framework organized the campaign like a military operation. The Hubble Space Telescope provided high-resolution visible imaging. Webb delivered infrared spectroscopy. Swift monitored ultraviolet emissions. TESS searched for brightness variations. Each telescope contributed unique capabilities, creating comprehensive coverage no single instrument could achieve. The European Space Agency mobilized its own assets. Ground-based telescopes in Chile's Atacama Desert took advantage of the world's clearest skies. The Very Large Telescope's 4 8-meter mirrors worked in concert. The European Southern Observatory coordinated observations across multiple facilities. Every clear night meant new data from the Southern Hemisphere. Asian observatories filled crucial gaps in temporal coverage. When the sun set in Chile, it rose over telescopes in Hawaii, Japan, and China. The Subaru Telescope, Keck Observatory, and Chinese Fast Radio Telescope ensured 24-hour monitoring. 3. I/ATLAS never left someone's sight until conjunction made observation impossible. Data sharing happened at unprecedented speeds. Observations uploaded to public archives within hours of collection. Analysis software was open-sourced, allowing anyone to process the data. Graduate students in India could analyze spectra taken in Chile. Amateur astronomers in Europe could access images from Hawaii. Geographic location became irrelevant. The International Astronomical Union's Minor Planet Center served as the central clearinghouse. Every position measurement, every orbital refinement flowed through their servers. They maintained the official trajectory, updated multiple times daily as new observations arrived. Their work ensured everyone studied the same object with the same parameters. Professional and amateur astronomers worked together seamlessly. While amateurs couldn't match professional telescope power, they provided valuable temporal coverage. Hundreds of smaller telescopes tracked 3 I/ATLAS nightly, alerting professionals to any sudden changes. The crowdsourced monitoring multiplied available eyes on the sky. Communication networks buzzed with activity. Dedicated Slack channels connected researchers worldwide. Telegram groups shared real-time updates. Academic Twitter became a continuous conference where discoveries were announced, discussed, and verified within hours. Traditional publication timescales compressed from months to days. The bandwidth demands were staggering. Terabytes of data flowed between continents daily. High-resolution images from Hubble, detailed spectra from Webb, continuous monitoring from ground observatories. The internet infrastructure of astronomy was pushed to its limits. Some observatories upgraded their connections specifically for 3 I/ATLAS. Funding agencies showed remarkable flexibility. Emergency grants were approved in days rather than months. Telescope time allocation committees met weekly instead of annually. Bureaucracy that usually moved at glacial pace suddenly operated at startup speed. Everyone understood this opportunity wouldn't come again. The collaboration extended beyond traditional astronomy. Chemists helped interpret molecular spectra. Physicists modeled gas dynamics. Computer scientists developed new analysis algorithms. Even historians contributed, comparing current observations to records of past comets. 3 I/ATLAS became truly interdisciplinary science. Language barriers were overcome through shared scientific vocabulary and translation tools. Papers appeared simultaneously in multiple languages. Video conferences included real-time translation. The global nature of the collaboration meant someone was always awake, always working, always pushing the analysis forward. Young scientists found unprecedented opportunities. Graduate students led observations at major telescopes. Postdocs coordinated international campaigns. Early career researchers published papers that would define their careers. 3 I/ATLAS democratized astronomy, giving everyone a chance to contribute to historic discoveries. The network's success provided a model for future rapid response astronomy. Protocols developed for 3 I/ATLAS would be refined and reused. The next interstellar visitor would trigger an even faster, more coordinated response. Every computer simulation of 3 I/ATLAS failed in the same way. The models could match some observations, but never all of them simultaneously. Fix the gas production rates, and the temperature was wrong. Adjust the composition to match spectra, and the cloud extent became impossible. The physics wasn't adding up. The standard comet model had worked for decades. Solar radiation heats the nucleus surface. Ice sublimates to gas. Gas drags dust particles into space. The process creates a coma around the nucleus and a tail pointing away from the sun. Simple physics, predictable behavior. Thousands of comets had followed these rules. But 3I/ATLAS broke every aspect of this model. The carbon dioxide production was too high for the nucleus size. The cloud extent was too large for the gas production rate. The temperature profile didn't match sublimation physics. Each observation added another impossibility to the list. The standard model wasn't just inadequate, it was fundamentally wrong for this object. Thermal models were the first to fail. Given 3I/ATLAS's size and distance from the Sun, physicists could calculate how much energy it received and how hot it should get. These temperatures determined sublimation rates for different ices, but the observed gas production exceeded theoretical maximum by factors of 10 or more. Gas dynamics simulations hit different problems. The expanding CO2 should follow predictable patterns based on molecular speeds and solar radiation pressure. Models predicted a compact coma, maybe tens of thousands of kilometers across. Instead, Spherex observed a cloud extending hundreds of thousands of kilometers. The physics couldn't explain such vast extent. Fragmentation models offered potential solutions but created new problems. If 3I/ATLAS was breaking apart, multiple fragments could produce more gas than a single nucleus. But fragmentation should be visible in images as multiple brightness centers or elongated structures. Hubble saw none of these signatures. The nucleus appeared single and stable. Dust dynamics added another layer of failure. The size and velocity of dust particles could be inferred from how they scattered light. These parameters should match the gas flow that lifted them from the surface. But the dust behaved independently from the gas, following different patterns that suggested separate ejection mechanisms. Some scientists proposed exotic solutions. Perhaps 3I/ATLAS had internal heat sources, radioactive decay, chemical reactions, or phase transitions that provided extra energy. These could drive sublimation beyond what solar heating allowed. But the required energy levels were enormous, implying compositions unlike any known comet. The layered structure hypothesis partially worked. If CO2, ice overlay water ice, differential sublimation could create the observed chemistry. But maintaining such layers through billions of years of space travel seemed unlikely. Cosmic radiation should have mixed the ices. Temperature cycling should have homogenized the structure. Electromagnetic effects were considered. If 3I/ATLAS carried electrical charge, interactions with the solar wind might accelerate gas beyond normal speeds. This could explain the extended cloud. But charged comets should show other signatures: emission lines from ionized gas, magnetic field perturbations. None were detected. Every model modification created new inconsistencies. It was like solving a puzzle where fixing one piece broke two others. The physics that explained the chemistry contradicted the dynamics. The structure that produced the observed activity couldn't survive interstellar travel. Nothing worked completely. The modeling failures suggested three possibilities. First, our physics might be incomplete, missing processes that operate in extreme conditions. Second, 3I/ATLAS might represent a class of objects never before observed, requiring entirely new theoretical frameworks. Third, multiple unusual processes might be operating simultaneously, creating complexity beyond current models. Computer clusters ran continuously, testing thousands of parameter combinations. Machine learning algorithms searched for patterns humans might miss. But no combination of known physics could reproduce all observations. 3I/ATLAS remained stubbornly impossible according to our theoretical understanding. The December observations would test whether models could predict post-perihelion behavior. If predictions failed again, it would confirm that our understanding was fundamentally flawed. The word terrifying in headlines about 3I/ATLAS was misleading. The object posed no physical threat to Earth. It would pass safely at 270 million kilometers, never coming close enough to affect our planet. The terror, if it existed, was entirely intellectual. It was the fear of discovering that our understanding of the universe was wrong. For decades, scientists had built comprehensive models of how comets work. These models explained thousands of observations across hundreds of objects. They predicted behaviors accurately. They guided spacecraft missions successfully. The physics seemed solid, complete, reliable. Then 3I/ATLAS arrived and shattered this confidence. The terror was paradigm collapse. When fundamental assumptions prove wrong, entire fields of study must be reconsidered. Textbooks become obsolete. Careers built on now false theories crumble. The comfortable certainty of established science evaporates. This intellectual upheaval can be genuinely frightening for those who experience it. Consider what 3I/ATLAS meant for planetary scientists. If comets could behave this differently, what else had we misunderstood? Were our models of planetary formation wrong? Had we misinterpreted observations of other comets? Did objects in our own solar system harbor similar surprises? The implications rippled outward endlessly. The carbon dioxide dominance alone challenged 50 years of comet science. Every paper about volatile ratios might need revision. Every model assuming water-dominated chemistry might be incomplete. Graduate students would need new thesis topics. Established professors would see their life's work questioned. The academic disruption was real. But there was excitement mixed with the fear. Science thrives on mystery. Unexplained observations drive progress. 3I/ATLAS offered the kind of fundamental puzzle that could launch entire careers. Young scientists saw opportunity where established researchers saw threat. The terror and thrill were inseparable. The public misunderstood the nature of this terror. Media headlines suggested physical danger or alien threats. But scientists worried about something more subtle. The possibility that nature was more complex than human minds could fully grasp. What if the universe contained phenomena that exceeded our cognitive capabilities? The extended gas cloud exemplified this worry. It wasn't just unexplained, it seemed impossible. No reasonable combination of known physics could produce it. Either we were missing something fundamental, or reality operated on principles we hadn't discovered. Both possibilities were unsettling. Historical parallels provided context. When radioactivity was discovered, it terrified physicists who thought they understood matter. When quantum mechanics emerged, Einstein himself resisted its implications. Each paradigm shift began with observations that seemed impossible, terrifying in their challenge to established thought. The interstellar origin amplified the psychological impact. 3I/ATLAS wasn't just an unusual comet from our solar system's edge. It came from an entirely different stellar environment. It represented chemistry and physics from places we could never visit. The unknown felt more unknown when it came from so far away. Some scientists embraced the terror as motivation. If our models were wrong, that meant new discoveries awaited. The universe was more interesting than we'd thought. Our ignorance was an opportunity for learning. The fear of the unknown transformed into curiosity about what we'd find. Others found the uncertainty paralyzing. How could you conduct research when fundamental assumptions were questionable? How could you teach students when textbooks might be wrong? The stable foundation of scientific knowledge felt suddenly unstable. The terror was vertigo from losing solid ground. The word terrifying ultimately said more about human psychology than about 3I/ATLAS itself. We fear what we don't understand. We're terrified when certainties become uncertainties. The cosmic visitor hadn't threatened our planet, but it had threatened our intellectual comfort. The real terror might be the possibility that 3I/ATLAS was just the beginning. If the first 3 interstellar visitors were this diverse and puzzling, what would the next dozen reveal? Every interstellar visitor was a free sample from another solar system's chemistry set. No space agency could retrieve material from other stars, but the universe delivered it to our doorstep. 3I/ATLAS carried billions of years of chemical history in its frozen nucleus, a laboratory experiment we could never replicate. The carbon dioxide dominance told stories about temperature and pressure conditions during formation. CO2 condenses at specific temperatures depending on ambient pressure. The abundance in 3I/ATLAS suggested formation environments that don't exist in our solar system. We were seeing chemistry from an alien laboratory with different experimental conditions. Each molecule detected was a piece of evidence about another star's protoplanetary disk. The ratios of different gases encoded information about temperature gradients, radiation fields, and chemical processes. It was like reading a recipe written in molecular language, describing how to build comets in foreign stellar kitchens. The preservation of these chemical signatures was remarkable. After billions of years in interstellar space, exposed to cosmic radiation that should scramble molecular structures, 3I/ATLAS still retained its original chemistry. The nucleus was a time capsule, sealed and delivered across galactic distances. Isotope ratios would be the ultimate prize. Different stellar environments produce different proportions of heavy to light isotopes. Carbon-13 to carbon-12 ratios could identify the type of star where 3I/ATLAS formed. Oxygen isotopes might reveal the temperature of formation. These measurements pushed instruments to their absolute limits. The chemical diversity across 3 interstellar visitors was striking. If 3 random samples showed such variety, the full population must span an enormous range. Every star system might produce its own chemical flavor of comets. The galaxy was a vast chemistry experiment with billions of different conditions. Laboratory work on Earth supported space observations. Scientists created ice mixtures matching 3I/ATLAS's supposed composition, subjected them to radiation and temperature cycles simulating billions of years in space. The experiments revealed unexpected chemistry, molecules that shouldn't exist, structures that shouldn't be stable. Photochemistry in the coma created new compounds in real time. Solar ultraviolet radiation broke apart parent molecules, creating radicals that recombined in novel ways. The coma wasn't just releasing stored chemistry. It was an active chemical reactor powered by our sun. We watched alien chemistry happening live. The missing water remained the biggest chemical puzzle. In our solar system, water was the universal solvent, the dominant ice, the key to comet activity. But 3I/ATLAS operated on different chemical principles. Either water was absent, hidden, or transformed into something we didn't recognize. Organic molecules added complexity. While major attention focused on CO2 and water, trace organics might tell even more interesting stories. Complex carbon chains, amino acid precursors, or other prebiotic molecules could reveal whether chemistry leading to life was common or rare in other stellar systems. The chemical laboratory of 3I/ATLAS operated at scales from molecular to astronomical. Individual molecules sublimated from microscopic ice grains. These collected into vast clouds hundreds of thousands of kilometers across. Chemistry connected the smallest and largest scales in ways that challenged understanding. Each spectrum captured was a page from an alien chemistry textbook. The infrared lines from Webb, the ultraviolet features from Swift, the visible light from ground telescopes. Together they told stories about conditions we could only imagine. Other stars, other temperatures, other possibilities. The December reappearance would reveal how perihelion changed the chemistry. Would heating release hidden compounds? Would thermal stress create new molecules? Would the chemical ratios evolve in predictable ways? The natural laboratory of solar heating would test our chemical understanding. The implications extended beyond astronomy. If chemistry was this diverse just among comets, what about planets? What about environments where life might arise? 3I/ATLAS expanded the chemical parameter space for everything we thought we knew about planetary systems. Before embracing exotic explanations, scientists exhausted every natural possibility. The strange behavior of 3I/ATLAS might result from conventional physics operating in unconventional conditions. The challenge was finding which combination of known processes could produce such apparently impossible observations. The radiation processing hypothesis had strong support. Billions of years of cosmic ray bombardment would fundamentally alter any exposed surface. High-energy particles could break molecular bonds, create new compounds, and build up crusts of processed material. Laboratory experiments showed that irradiated ices developed properties very different from pristine samples. Such processing could explain the carbon dioxide dominance. If radiation preferentially destroyed water molecules while preserving CO2, or converted other compounds into CO2, the observed ratios might result. The process would be slow but inevitable over geological timescales. Time itself became a chemical reagent. The insulating mantle model addressed multiple mysteries. If 3I/ATLAS developed a dust layer during its interstellar journey, this could trap heat and gases in unusual ways. The mantle might allow CO2 to escape through cracks while keeping water sealed beneath. This selective permeability could produce the observed chemistry. Temperature gradients within the nucleus offered another angle. If the interior remained colder than the surface, different ices would sublimate at different depths. CO2 from outer layers, water trapped in the frozen core. The structure would be like an onion with chemical layers instead of physical ones. The fragmentation hypothesis, while problematic, couldn't be dismissed. Perhaps 3I/ATLAS was shedding small chunks continuously, each one contributing to the extended gas cloud. These fragments might be too small to detect individually, but collectively significant. The nucleus would be slowly dissolving rather than sublimating. Amorphous ice transformation provided another mechanism. In the extreme cold between stars, water ice could exist in a glassy, non-crystalline state. When warmed by our sun, this amorphous ice might transform to crystalline forms, releasing energy that drove unusual outgassing patterns. The phase transition could explain excess activity. Differential sublimation based on grain size was considered. If CO2 existed as tiny grains while water formed larger chunks, the surface area difference would favor CO2 sublimation. This grain size segregation might arise naturally during formation or develop through billions of years of thermal cycling. The electrostatic levitation model proposed that charged dust particles could hover above the surface, extending the apparent size of the active region. Solar-wind interactions might charge the particles, creating complex electromagnetic effects. This could explain the extended cloud without requiring impossible gas production rates. Clathrate structures offered intriguing possibilities. These cage-like arrangements of water molecules could trap CO2 in high concentrations. When heated, clathrates might release CO2 preferentially while maintaining their water framework. This chemistry was known from Earth's ocean floors, but never observed in comets. The primordial composition hypothesis suggested 3I/ATLAS simply formed differently. Its parent star system might have had unusual carbon-to-oxygen ratios, temperatures that favored CO2 over water, or formation mechanisms that concentrated specific ices. We were seeing normal chemistry from an abnormal environment. Each natural explanation had strengths and weaknesses. Radiation processing was inevitable, but might not produce observed ratios. Insulating mantles could form, but should be visible in images. Fragmentation would show other signatures. No single mechanism explained everything, but combinations might work. The scientific method demanded testing these natural hypotheses before considering alternatives. Each model made specific predictions about post-perihelion behavior. The December observations would eliminate some possibilities and strengthen others. Natural explanations remained favored until proven inadequate. The challenge was that 3I/ATLAS pushed natural processes to extremes. Even if conventional physics could explain the observations, the required conditions were so unusual that they barely seemed natural. The boundary between natural and exotic became blurry at such extremes. December would bring the moment of truth. As 3I/ATLAS emerged from behind the Sun, every telescope would search for changes that confirmed or rejected competing theories. The perihelion passage was nature's experiment, testing our ideas with solar heat and radiation. The natural sublimation model made specific predictions. If conventional physics governed 3I/ATLAS, the CO2 to water ratio should evolve predictably. Higher temperatures at perihelion might break through insulating layers, releasing trapped water. The ratio should shift toward more normal values. If it didn't, the model was wrong. Fragmentation scenarios could be tested through imaging. If perihelion's thermal stress shattered the nucleus, December observations should reveal multiple components. The brightness profile would be extended or irregular. Multiple peaks might appear in the coma. High-resolution imaging would show a destroyed or damaged nucleus. The extended cloud's evolution would test gas dynamics models. If the enormous CO2 envelope resulted from accumulated emissions, it should begin dissipating after perihelion. The cloud should shrink as production decreased, and solar winds swept away existing gas. Continued growth would demand new explanations. Spectroscopic monitoring would reveal chemical changes. New molecules might appear as different ices became active. Isotope ratios might shift if deeper layers with different compositions were exposed. The spectrum would be a chemical fingerprint of what perihelion had done to the nucleus. Rotational changes would indicate structural alterations. If outgassing torques or fragmentation changed the nucleus's spin, the light curve would evolve. New periodicities might emerge. Chaotic tumbling could begin. The rotation state would reveal mechanical changes invisible in direct imaging. Temperature measurements would test thermal models. The cooling rate after perihelion would indicate thermal inertia and internal structure. Rapid cooling suggested a small solid nucleus. Slow cooling implied larger size or unusual thermal properties. The temperature curve would constrain physical models. Any detection of non-gravitational acceleration would be crucial. If 3I/ATLAS began showing trajectory deviations like Oumuamua, it would suggest similar processes despite different compositions. The magnitude and direction of acceleration would reveal what forces were operating. The hydroxyl mystery needed resolution. If water was present but hidden, maximum heating should have released it. December spectra should show strong water signatures if the suppression hypothesis was correct. Continued absence would mean water truly was depleted. Dust properties would provide structural clues. The size distribution, composition, and velocity of ejected particles would indicate how the nucleus was constructed. Large chunks suggested fragmentation. Fine dust implied gentle sublimation. The dust would tell stories about the unseen nucleus. Activity patterns at large distances would test sublimation models. As 3I/ATLAS receded from the Sun, which ices remained active? Did CO2 production continue at distances where it should freeze? Unusual activity at large distances would point toward internal energy sources or exotic compositions. The comparison with pre-perihelion observations would be critical. What changed and what stayed the same? Permanent alterations suggested structural damage. Temporary changes implied reversible processes. The before and after comparison would reveal perihelion's true impact. Each telescope would contribute specific tests. Webb would search for new molecules. Hubble would map morphological changes. Ground observatories would track brightness evolution. The combined observations would create a comprehensive picture of post-perihelion 3I/ATLAS. The scientific community prepared for any outcome. If 3I/ATLAS emerged unchanged, it would suggest remarkable structural stability. If it showed dramatic alterations, those changes would reveal internal properties. Even fragmentation or complete destruction would provide valuable data about composition and structure. The tests were carefully designed to be decisive. Each theory made falsifiable predictions that December observations could evaluate. This wasn't speculation, but rigorous hypothesis testing. The Vera C. Rubin Observatory would revolutionize interstellar object science starting in 2025. Its 8.4-meter mirror and 3.2 gigapixel camera would survey the entire southern sky every 3 nights. This unprecedented capability would transform rare interstellar visitors into routine discoveries. The numbers were staggering. Current surveys detected 1 interstellar object every few years. Rubin was expected to find 10 to 70 annually, depending on the true population density. Within a decade, we would go from 3 known visitors to potentially hundreds. Statistics would replace anecdotes. The survey strategy was optimized for discovery. Unlike targeted observations of known objects, Rubin would continuously scan vast sky areas. Its automated detection algorithms would flag anything moving unusually fast or on hyperbolic trajectories. Interstellar visitors would be identified within days of becoming visible. Early detection would be game-changing. Instead of discovering visitors as they left, like Oumuamua, Rubin would find them years before perihelion. This lead time would allow detailed mission planning, instrument preparation, even spacecraft intercepts. We would be ready for visitors instead of scrambling to respond. The population statistics would answer fundamental questions. Were carbon dioxide-dominated objects like 3I/ATLAS common or rare? Did most visitors resemble normal comets like Borisov? How many were inactive like Oumuamua? The answers would reveal what types of objects survived interstellar journeys. Size distributions would constrain formation models. If small objects dominated, it suggested collisional grinding in their parent systems. Large objects implied gentle ejection processes. The size spectrum would encode information about dynamics in alien planetary systems. Chemical diversity assessments would map the galaxy's composition. Each visitor's spectrum would add another data point to our chemical atlas. Patterns might emerge, objects from certain directions showing similar compositions, suggesting common formation regions. The galaxy's chemical geography would be revealed. Orbital characteristics would trace galactic structure. The trajectories of hundreds of visitors would map the local velocity field. Patterns in their origins might reveal stellar streams, moving groups, or other galactic structures. Interstellar objects would become probes of galactic dynamics. The alert system would enable rapid response. Within hours of detection, Rubin would distribute orbital elements to observatories worldwide. Automated systems would trigger follow-up observations. The global response that took weeks for 3I/ATLAS would happen in hours for future visitors. Statistical rare events would become observable. If 1 in 100 visitors showed truly anomalous behavior, we would need to observe hundreds to find it. Rubin would provide that sample size. The weird outliers that might revolutionize understanding would be discovered. Cross-correlation with other surveys would multiply scientific value. Objects detected by Rubin could be observed by Webb, studied by radio telescopes, monitored by amateur networks. The multi-wavelength, multi-instrument approach developed for 3I/ATLAS would become standard practice. Machine learning would be essential for processing Rubin's data flood. Artificial intelligence would identify candidates, classify objects, and flag anomalies. Human astronomers would focus on the most interesting cases. The partnership between human insight and machine efficiency would accelerate discovery. The archival value would be immense. Every Rubin observation would be permanently stored, searchable, and reanalyzable. Future scientists could mine this data for patterns invisible to current analysis. Today's mysteries might be solved by tomorrow's techniques applied to Rubin's vast database. Young scientists would build entire careers on Rubin data. Graduate students would have access to discoveries that previously defined whole careers. The democratization of astronomical discovery would accelerate. Geography and institutional affiliation would matter less than creativity and dedication. The transition from 3I/ATLAS to the Rubin era represented a phase change in interstellar object science. We were moving from individual case studies to population analysis, from anecdotes to statistics, from surprises to patterns. The European Space Agency's Comet Interceptor would be humanity's first spacecraft designed specifically for interstellar visitors. Launching in 2029, it would wait at the L2 Lagrange point, 1.5 million kilometers from Earth, ready to intercept targets of opportunity. When the next 3I/ATLAS arrived, we would be prepared. The mission design was revolutionary. Traditional spacecraft were built for specific targets with known orbits. Comet Interceptor would launch without knowing its destination. It would park at L2, possibly for years, until a suitable target appeared. Then it would spring into action, racing to intercept an object never before seen. The spacecraft consisted of 3 modules. The main spacecraft would carry primary instruments and communication systems. 2 smaller probes would separate during approach, providing multiple viewing angles and redundancy. If one probe was destroyed by debris, others would continue observing. The instrument suite was optimized for brief, high-speed encounters. Cameras would capture surface details during the minutes of closest approach. Spectrometers would analyze composition in real time. Dust analyzers would directly sample material ejected from the nucleus. Every instrument was designed for split-second science. The targeting flexibility was crucial. Comet Interceptor could redirect toward any object passing within reasonable range. An interstellar visitor, a long-period comet, even an unusual asteroid. The mission would wait patiently for the most scientifically valuable target, whether from our solar system or beyond. Navigation challenges were extreme. Intercepting a fast-moving, poorly characterized object required autonomous systems. The spacecraft would need to identify the target, refine its trajectory, and adjust course in real time. By the time signals reached Earth, the encounter would be over. The science objectives focused on fundamental questions. What were interstellar objects made of? How did they survive journeys between stars? Were they fundamentally different from solar system comets? Direct sampling would provide answers that remote observation never could. Risk tolerance was necessarily high. The spacecraft might impact debris, be destroyed by outgassing jets, or miss the target entirely. These risks were acceptable given the scientific value of success. One good encounter would justify multiple mission attempts. International collaboration was built into the mission framework. ESA led development, but instruments came from institutions worldwide. Data would be immediately public. The entire global scientific community would participate in analysis. Comet Interceptor embodied the collaborative spirit shown during 3I/ATLAS observations. The wait at L2 would be productive. While stationed there, Comet Interceptor could observe other astronomical phenomena. The stable thermal environment and distance from Earth made it an excellent platform for various observations. The spacecraft would contribute to science even before its primary mission. Target selection would be challenging. Multiple factors would be weighed: scientific value, intercept feasibility, risk level. An interstellar visitor would be highest priority, but a particularly unusual comet might be selected instead. The decision would balance opportunity against patience. The legacy of 3I/ATLAS influenced every aspect of Comet Interceptor's design. Lessons learned about rapid response, international coordination, and critical measurements shaped mission planning. The mysteries that 3I/ATLAS left unsolved became Comet Interceptor's primary objectives. Success would transform interstellar object science. Direct sampling of material from another star system would provide ground truth for all spectroscopic observations. Isotope ratios, mineral structures, organic compounds could be measured precisely. the gap between remote sensing and laboratory analysis would be bridged. The mission represented humanity's commitment to understanding interstellar visitors. Instead of being caught unprepared, we would have a dedicated sentinel waiting. The next three, I/ATLAS, wouldn't slip away unstudied. The discovery of 3I/ATLAS forced humanity to confront a new reality. The space between stars wasn't empty, but populated with wandering fragments of distant worlds. Our solar system wasn't isolated, but part of a vast network where material regularly crossed between stellar systems. The galaxy was more connected than we imagined. This galactic exchange had been happening for billions of years. While Earth developed life and civilization, countless interstellar objects passed through our solar system unnoticed. Some might have impacted planets or moons, delivering alien chemistry to our worlds. We had been receiving cosmic mail without knowing it. The numbers were humbling. Models suggested that several interstellar objects passed within Earth's orbit every year. Hundreds crossed Neptune's orbit annually. The galaxy was full of nomadic wanderers, ejected from their birth systems to drift forever between stars. Our solar system was constantly hosting invisible visitors. Each object carried information about its origin. The chemistry encoded formation conditions. The structure revealed processing history. The trajectory traced back to stellar neighborhoods we could never visit. These weren't just rocks and ice, but messages from across the galaxy. The timescales involved challenged human comprehension. 3I/ATLAS had been traveling since before our solar system existed. It had witnessed stellar evolution, supernova, the birth and death of planetary systems. This single object connected us to the galaxy's deep history in tangible ways. The preservation of volatile ices across such timescales was remarkable. In the cold between stars, protected from stellar radiation, these cosmic wanderers maintained their chemical cargo nearly intact. They were time capsules, delivering ancient materials to whoever happened to observe their passage. The diversity revealed by just 3 visitors suggested enormous variety awaited discovery. If random sampling produced such different objects, the full population must span incredible ranges of composition, structure, and behavior. Every stellar system might produce unique flavors of cosmic debris. The implications for panspermia were intriguing. If objects regularly traveled between star systems, could they carry more than just chemistry? Organic molecules, perhaps even dormant microorganisms, might hitchhike across the galaxy. Life might spread through interstellar impacts, seeding worlds with biological potential. Our solar system had probably ejected its own objects into interstellar space. During planetary formation, gravitational interactions would have scattered countless comets and asteroids onto escape trajectories. Somewhere in the galaxy, fragments of our solar system were visiting alien stars. This reciprocal exchange meant stellar systems weren't closed boxes, but open networks. Material and information flowed between stars on geological timescales. The galaxy was engaged in slow but steady commerce, trading samples of planetary formation across vast distances. The detection capability that revealed 3I/ATLAS was very recent. Only in the last decade had surveys become sensitive enough to routinely find interstellar visitors. We were living at the precise moment when humanity became aware of this cosmic exchange. Earlier generations couldn't have known. Future ones would take it for granted. The philosophical impact was profound. Earth wasn't special or isolated, but part of a galactic community. Our solar system regularly interacted with others through these wandering ambassadors. We were connected to distant stars through threads of ice and rock crossing the void. The search for life gained new dimensions. Instead of just looking for radio signals or exoplanets, we could study actual samples from other stellar systems. Each interstellar visitor might carry chemical hints about biological potential elsewhere. The galaxy might be telling us about life through these messengers. The cosmic perspective transformed how we saw our place in the universe. We weren't alone on an island, but part of an archipelago connected by streams of cosmic debris. 3I/ATLAS was just one thread in a vast web binding the galaxy together. The investigation of 3I/ATLAS showcased science at its best and most challenging. Extraordinary claims require extraordinary evidence, and this interstellar visitor made claims through its very existence that challenged established science. The response revealed how science self-corrects when faced with anomalies. Initial observations triggered healthy skepticism. The carbon dioxide dominance seemed impossible. Many astronomers assumed measurement error or calibration problems. But independent confirmation from multiple observatories using different instruments eliminated technical explanations. The anomaly was real. Competing hypotheses emerged immediately. Each research group proposed different explanations for the strange chemistry and enormous gas cloud: natural sublimation, fragmentation, radiation processing, exotic ices. The diversity of ideas reflected creative thinking unconstrained by premature consensus. Falsifiable predictions distinguish science from speculation. Each hypothesis made specific claims about what future observations would reveal. These predictions could be tested and rejected if wrong. The scientific method demanded that ideas face observational reality. Data sharing accelerated progress. Instead of hoarding observations for exclusive papers, astronomers released data immediately. This openness allowed rapid verification and reanalysis. Errors were caught quickly. Patterns emerged from combined datasets that no single observation could reveal. Peer review operated in real time. Traditional journals were too slow for rapidly evolving discoveries. Preprint servers allowed immediate publication. Social media enabled instant feedback. The community collectively evaluated claims within hours instead of months. Mistakes were acknowledged openly. When initial reports suggested features that later observations disproved, corrections were published immediately. Science progressed through error correction, not perfection. The willingness to be wrong enabled eventual understanding. Interdisciplinary collaboration was essential. Astronomers alone couldn't explain 3I/ATLAS. Chemists contributed molecular expertise. Physicists modeled gas dynamics. Computer scientists developed analysis algorithms. The mystery demanded diverse perspectives. Young scientists challenged established authorities. Graduate students proposed ideas that senior professors initially rejected. Fresh perspectives, unconstrained by decades of assumptions, sometimes saw solutions that experience missed. The hierarchy of expertise became fluid. Uncertainty was embraced rather than hidden. Scientists openly admitted what they didn't understand. Press releases included caveats and qualifications. The public saw science as a process of discovery rather than a source of absolute truth. Incremental progress accumulated into understanding. Each observation added constraints. Each failed model eliminated possibilities. The path to truth was indirect, meandering through wrong turns and dead ends. But each step brought clarity. The null hypothesis remained respected. Despite the mysteries, most scientists maintained that natural explanations would eventually emerge. Exotic proposals were entertained, but required higher standards of evidence. Ordinary claims needed ordinary evidence. Extraordinary claims needed more. Technology and theory advanced together. New observational capabilities revealed phenomena that existing theories couldn't explain. This drove theoretical development, which suggested new observations. The cycle of observation and explanation accelerated understanding. The human element remained central. Behind every discovery were people working exhausting hours, facing frustration and failure, experiencing the joy of breakthrough. Science was ultimately a human endeavor, driven by curiosity and sustained by dedication. The process wasn't always pretty. Disagreements sometimes became personal. Competition for credit created tensions. Funding pressures influenced research directions. But despite human flaws, the scientific method worked. Truth emerged from collective effort. 3I/ATLAS demonstrated that science could respond rapidly to unprecedented phenomena. The global coordination, open collaboration, and intellectual flexibility shown during this investigation would serve as a model for future discoveries. Stripping away sensationalism and headlines, Webb's actual discoveries about 3I/ATLAS were remarkable enough without exaggeration. The telescope had revealed chemistry that challenged models, behaviors that defied physics, and mysteries that remained unsolved. The truth was more interesting than fiction. The carbon dioxide dominance was confirmed beyond doubt. Webb's infrared sensitivity detected CO2 emission lines, with signal-to-noise ratios that eliminated uncertainty. The 8:1 ratio with water wasn't measurement error or calibration artifact. It was real, verified, and demanding explanation. Water ice signatures appeared in reflection spectra, showing it existed on or near the surface. But water vapor was nearly absent from emission spectra. This contradiction meant water was present but not sublimating efficiently. Something was preventing normal comet behavior. The temperature measurements revealed thermal properties inconsistent with simple ice models. The nucleus was warmer than pure ice should be at that distance, but cooler than dark rocky material. The thermal inertia suggested complex structure, possibly layered or porous. Organic molecule detections added complexity. Webb found signatures of complex carbon chains, possibly including aromatic compounds. These organics might be primordial, formed in the original protoplanetary disk, or products of billions of years of radiation processing. The spatial distribution of emissions showed unexpected structure. Instead of uniform outflow from the nucleus, gas emerged in jets and streams. These patterns suggested active regions on the surface, specific locations where sublimation was enhanced. Isotope ratios, though difficult to measure precisely, hinted at formation in environments different from our solar system. The carbon and oxygen isotope patterns didn't match solar values. This supported an origin in another stellar system with different nucleosynthetic history. Temporal variations in the spectra revealed dynamic processes. The emission lines strengthened and weakened over hours to days. This variability suggested changing activity levels, possibly related to rotation or episodic outbursts. The extended wavelength coverage revealed features invisible to other telescopes. Far-infrared emissions that traced cold dust. Near-infrared absorptions from ices not yet identified. Webb saw aspects of 3I/ATLAS that no other instrument could detect. Cross-correlation with other observations multiplied the value. Webb's chemical data combined with Hubble's imaging and SphereX's mapping created multidimensional understanding. Each telescope contributed pieces that together formed a more complete picture. The precision achieved was remarkable given the challenges. 3I/ATLAS was faint, fast-moving, and observed at extreme solar elongations. Yet Webb delivered spectra with quality, matching much easier targets. The technical achievement was as impressive as the scientific results. What Webb didn't find was equally important. No exotic molecules that screamed artificial origin. No spectral signatures completely outside known chemistry. No behaviors that required abandoning physics. The mysteries were real, but potentially solvable. The uncertainties were honestly acknowledged. Some spectral features remained unidentified. Some behaviors lacked good explanations. Some measurements had large error bars. Webb revealed mysteries without pretending to solve them all. The data would remain valuable for decades. As theoretical understanding improved, researchers would return to Webb's observations with new analysis techniques. Details overlooked initially might prove crucial later. The archival value was immense. Webb had done exactly what great observatories should do: reveal nature as it is, not as we expect it to be. The telescope showed us an interstellar visitor that challenged assumptions and demanded new thinking. December 5th, 2025. After 2 months of agonizing blindness, 3I/ATLAS emerged from behind the Sun. Every major telescope on Earth's night side turned toward the constellation Virgo, where our interstellar visitor would reappear. The wait was over. The moment of truth had arrived. First light came from the Subaru telescope in Hawaii. The initial images showed 3I/ATLAS had survived perihelion intact. No massive fragmentation, no catastrophic disruption. The nucleus remained single and stable. But changes were evident even in those first glimpses. The coma appeared larger, more diffuse. Something had happened during conjunction. Webb's first post-conjunction spectrum revealed evolution in the chemistry. The carbon dioxide emissions remained strong, but new features appeared. Water vapor, nearly absent before, now showed clearly. The heating had finally broken through whatever was suppressing water sublimation. The ratio had shifted from 8:1 to roughly 4:1, still CO2 dominated, but less extremely. The extended gas cloud had grown even larger. SphereX mapped CO2 emissions stretching nearly 500,000 kilometers from the nucleus. This defied predictions that post-perihelion activity would decrease. Instead of shrinking as it cooled, the cloud was expanding. The physics remained mysterious. Hubble's high-resolution imaging revealed structural changes in the coma. The previously smooth distribution now showed clumps and streams. These features suggested material was being released in discrete events rather than continuous sublimation. The nucleus might be shedding chunks too small to resolve, but large enough to affect gas distribution. Temperature measurements showed unexpected cooling rates. The nucleus was losing heat faster than models predicted, suggesting higher thermal conductivity than typical cometary ice. This might mean the interior was more consolidated, less porous than assumed. The thermal behavior added another constraint on composition models. The hydroxyl production had increased dramatically. Swift detected OH emissions at levels consistent with significant water vapor, finally reconciling the earlier contradiction. Whatever mechanism had trapped water before perihelion had been overcome by solar heating. The chemistry was evolving toward more normal comet behavior. Rotational analysis revealed the spin had changed. The periodicity and brightness variations was different from pre-conjunction observations. Outgassing torques during perihelion had altered the rotation state. The new spin was complex, possibly indicating non-principal axis rotation or tumbling. New organic features appeared in infrared spectra. Webb detected emission lines from molecules not seen before conjunction. These might be products of thermal processing during perihelion, or materials from deeper layers now exposed. The organic chemistry was richer than initially realized. Dust production had shifted to larger particles. The scattered light properties indicated bigger grains than before perihelion. This might result from sintering during maximum heating, causing small particles to stick together. Or deeper layers might naturally produce larger dust. The trajectory showed tiny but measurable deviations from gravitational predictions. 3I/ATLAS was experiencing non-gravitational acceleration, though much smaller than Oumuamua's. The force was consistent with asymmetric outgassing, jets pushing the nucleus in preferred directions. Activity remained high despite increasing distance from the Sun. At distances where normal comets would be shutting down, 3I/ATLAS continued vigorous emission. This suggested either very volatile composition or continued heat release from the interior. As December progressed, the observation window was shrinking. Each night, 3I/ATLAS was farther away, fainter, harder to study. The race against distance resumed, but the post-conjunction observations had been invaluable. They showed how perihelion had transformed our visitor, revealing properties hidden during approach. The changes confirmed that 3I/ATLAS was actively evolving, not a static object. The solar encounter had triggered processes that continued affecting its behavior. We were watching real-time processing of interstellar material by our Sun. The global response to 3I/ATLAS revealed humanity at a crossroads between cosmic provincialism and galactic awareness. For the first time, our species had mobilized worldwide resources to study a confirmed visitor from another star. The coordination achieved and lessons learned would shape how we approach future cosmic encounters. International cooperation had reached unprecedented levels. Nations that rarely collaborated on Earth worked together in space. Data flowed freely across borders that usually restricted information exchange. The cosmic perspective had temporarily transcended terrestrial politics. Public engagement surpassed all previous astronomical events, except perhaps the Apollo missions. Museums created exhibits about interstellar visitors. Planetariums updated shows to include 3I/ATLAS. Schools incorporated the discovery into curricula. The visitor had become a cultural phenomenon beyond scientific circles. Amateur astronomers had contributed more than expected. While 3I/ATLAS remained too faint for most amateur equipment, dedicated observers with larger telescopes provided valuable temporal coverage. Their observations filled gaps when professional telescopes were unavailable. Citizen science had proven its worth. The media coverage had been mixed. Responsible outlets had conveyed the genuine wonder while avoiding sensationalism. But clickbait headlines about terrifying discoveries and alien technology had spread misinformation. The challenge of accurate science communication in the social media age was starkly revealed. Funding agencies had responded with remarkable agility. Emergency grants were approved in record time. Telescope time allocation committees had shown unprecedented flexibility. Bureaucracies that normally moved glacially had operated at startup speeds. The urgency of the opportunity had overcome institutional inertia. Educational impacts would last generations. Students who learned about 3I/ATLAS would carry that wonder throughout their lives. Some would become scientists inspired by this first glimpse of interstellar material. The visitor had planted seeds that would bloom decades later. The technological development spurred by 3I/ATLAS would benefit all astronomy. Improved spectrometers, faster data processing, better coordination protocols. The tools developed for this crisis would enhance regular observations. Crisis-driven innovation had created lasting capabilities. Philosophical and religious institutions had grappled thoughtfully with implications. The discovery that material regularly traveled between star systems had theological ramifications. Our cosmic isolation was ending. Earth was part of a galactic community whether we were ready or not. The economic impacts were subtle but real. Aerospace companies had seen stock fluctuations. Educational institutions had experienced enrollment changes. The space economy had received validation that cosmic events could drive terrestrial economics. Social movements had emerged around the discovery. Groups advocating for increased space funding, for international cooperation, for cosmic perspective in policymaking. 3I/ATLAS had become a rallying point for those who believed humanity needed to think beyond Earth. The psychological impact varied by culture and generation. Younger people seemed to accept interstellar visitors as natural, even expected. Older generations found the implications more unsettling. The cosmic perspective shift was happening at different rates across society. Political leaders had largely avoided exploiting the discovery for partisan purposes. Perhaps the cosmic scale made terrestrial politics seem petty. Or maybe the international nature of the discovery prevented national appropriation. The visitor belonged to all humanity. The scientific community had demonstrated remarkable unity despite competitive pressures. Credit had been shared generously. Disputes had been resolved professionally. The importance of the discovery had overcome individual egos. Looking forward, humanity was better prepared for the next visitor. Protocols had been established, networks created, capabilities developed. When the next interstellar object arrived, response would be faster and more effective. The legacy of 3I/ATLAS extended beyond scientific data. It had shown humanity could unite around cosmic discoveries. It had proven our species capable of planetary-scale coordination. It had demonstrated that wonder could transcend borders. As 3I/ATLAS faded into the cosmic distance, racing back toward the darkness between stars, humanity was left to contemplate what this visit had meant. The scientific data would be analyzed for years, but the broader implications would resonate for generations. We had learned that the universe was far more chemically diverse than our provincial solar system had suggested. 3 interstellar visitors had shown 3 completely different compositions. The galaxy was a vast chemistry experiment with billions of different conditions producing varieties of matter we had never imagined. The concept of isolation had ended. Earth was not alone in empty space, but surrounded by streams of interstellar debris. Material from other star systems passed through regularly. We were part of a galactic ecosystem where matter and perhaps information flowed between stellar systems on geological timescales. Our theoretical frameworks had proven inadequate. Models based on solar system examples had failed when confronted with genuinely alien objects. The universe contained phenomena that exceeded our current understanding. This wasn't terrifying, but exciting. New mysteries meant new discoveries awaited. The importance of preparation had been demonstrated. We had caught 3I/ATLAS at a fortunate moment, but still scrambled to observe it effectively. Future visitors deserved better preparation. The Rubin Observatory and Comet Interceptor mission represented humanity's commitment to being ready. International cooperation had achieved remarkable successes. When faced with cosmic opportunities, humanity could transcend its divisions. The coordination achieved for 3I/ATLAS provided a model for addressing other global challenges. Cosmic perspective could unite our species. The value of open science had been validated. Immediate data sharing had accelerated discovery. Collaborative analysis had revealed patterns no single team would have found. Transparency had built public trust. Science worked best when practiced openly. Young scientists had found unprecedented opportunities. The rapid pace of discovery had created spaces for new voices. Established hierarchies had become fluid. Merit mattered more than seniority. The next generation had proven ready for cosmic challenges. Technology had advanced through necessity. The demands of studying 3I/ATLAS had pushed instruments and algorithms to new capabilities. These improvements would benefit all astronomy. Crisis-driven innovation had created lasting progress. Public engagement had reached new heights. Ordinary people had followed a scientific investigation in real time. Complex concepts had been communicated successfully. The public had shown appetite for genuine cosmic wonder without sensationalism. The questions raised were more valuable than answers found. Why was 3I/ATLAS so CO2-rich? How did it maintain such an enormous gas cloud? What would the next visitor reveal? Good questions drove science forward more than premature answers. The cosmic perspective had shifted subtly but significantly. Earth was not the center of the universe, not unique, not isolated. We were one world among countless others, all sharing material through interstellar exchange. This knowledge was humbling but also connecting. The future looked different now. As telescopes turned toward other targets and 3I/ATLAS disappeared into darkness, humanity faced a universe known to be populated with wanderers between stars. Each one carried messages from places we could never visit, chemistry we had never seen, stories we had barely begun to read. The terror mentioned in headlines had never materialized. Instead, we had found wonder. The universe was stranger than we had imagined, more connected than we had known, more generous with its secrets than we had dared hope. 3I/ATLAS had been a teacher, showing us how much we still had to learn. As you drift towards sleep, consider that right now, other interstellar visitors are approaching our solar system. They carry their own mysteries. their own impossible chemistry, their own challenges to our understanding. When they arrive, we'll be ready. The universe keeps sending us messages. We're finally learning how to read them. The story of 3I/ATLAS was ending, but the story of humanity's relationship with interstellar visitors had just begun. Sweet dreams, and remember, we are not alone in the cosmos. We never were.